Alright, hello everyone. My name is Anirudh Govada, and today I'm going to show you like a really cool limit concept that I found out and I looked at earlier. So as we know, when we're taking a limit of a number, let's say I have a limit as x approaches c of, let's say, L. We're trying to find what is L approaching as x approaches the c number here. So keeping that in mind, but we also have some expressions where we get like an indeterminate form. Let's say if I ask you to find the limit as x approaches 0 of, for example, sine x over x. Usually the normal way of doing limits like this is we do a direct substitution. But if we do a direct substitution, this will equal sine 0, which is 0, over 0, which we consider to be an indeterminate form. So instead of doing that, we're going to use something called L'Hopital's rule. So there's also a fundamental trig identity that you need to know. But the way that you come up with the answer is you use something known as L'Hopital's rule. So I'm going to open a new section here. So if we have a limit as x approaches 0, sine x over x. Now what L'Hopital's rule is saying is you're going to find the limit by taking a derivative. And L'Hopital's rule only works if you are using a limit which has an indeterminate form when you use direct substitution. So when I'm using L'Hopital's rule, I'm going to take the derivative of the top and the bottom. And so when I take the derivative, I get the derivative of sine x, which is just equal to cosine x. So I'm going to keep the limit sign, I'm going to keep the limit notation carried forward. So I'm going to have cosine x, I differentiated sine x, and if I differentiate x, the derivative of x is 1 with respect to x. So now I can do a direct substitution, because now cosine 0 is actually 1, so this is going to be equal to 1 over 1, or 1. So if we go back to the original problem here, we found out the limit as x approaches 0 of sine x over x is equal to 1. And we found out only because we were able to apply L'Hopital's rule, which says that you are going to take the derivative of both the numerator and denominator in order to find the limit. So if we want to generalize this, let's say if I have the limit as x approaches a constant c of f of x over g of x, where if I do direct substitution, f of c is equal to 0, and g of c is equal to 0 as well, then I can say that this is also equal to the limit as x approaches c of the derivative of f of x over the derivative of g of x. Or that's how the prime notation works there. So this is a general form of L'Hopital's rule. Look it up. There's Wikipedia. There's links everywhere. But this is the general notation that we'll use. And we saw a perfect example here with sine x over x, which is a very classic L'Hopital's problem that you'll find out. And this is a very fundamental trigonometric limit that you should memorize. You have to memorize this in future calc classes. So now we're going to extend this, and we're going to look at another limit along the lines of this. But instead of having the limit as x approaches 0, we're going to have the limit as x approaches infinity. So we're going to get limits as x approaches infinity. And this is the limit x sine of 1 over x. So if you look at this, this looks really complicated at first because you have the 1 over x here. But we're going to use the same pattern that we saw sine x over x, and then we're going to try to convert this into this kind of form, because now we know that sine x over x equals 1. So we can also generalize that by saying sine like nx over nx with the limit as x approaches 0, though. Cannot be infinity, has to be 0 equals 1. So make sure we have that in mind. So but we have a limit as x approaches infinity here, not 0. So we gotta be very, very careful. So what I'm gonna do is I'm gonna take this x right here. And I'm gonna put it in the denominator. So I'm gonna create a top and a bottom. So how that works is gonna be limit as x approaches infinity. I'm gonna have sine 1 over x here, and I'm going to have a denominator of 1 over x. And this is equivalent because if you multiply by x over x, this goes away, and you'll have x times sine of 1 over x. So this is still equivalent, so just want to show you that. Okay, so we have 1 over x here, and now we have the form of sine of something here, sine of like a constant over a constant, or like sine of like an expression over an expression. And we know that but we have to look at this part. This is actually x equals infinity. The limit is approaching to infinity and not 0. So how can we approach this way to make this equal to 0? So if we, let's say I'm going to use a substitution. I'm going to use the variable, let's say alpha, beta, but let's use theta. So I'm going to try and show up here. So let's have the limit. So before I do that, I'm gonna say let theta equal 1 over x. So if x is approaching infinity, that means 1 over infinity is going to be 0. No, x does not get to infinity, x is approaching infinity, but when you have a constant over a very, 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 very large number, this is going to be approaching 0. So instead of saying to limit as x approaches infinity, I can also say equal to the limit as theta approaches 0, because x approaches infinity here. This is basically 1 over infinity, which theoretically equals 0. So now we can use the same thing, and keeping in mind that 1 over x is actually going to get replaced with theta. So 1 over x is going to get replaced with theta. So now that we have limit as theta approaches 0 of sine theta over theta. Now, considering what we have at the very, very beginning, sine x over x, as x approaches 0, we found that to be 1. And by using the same L'Hopital's rule or just recognizing the problem, now that we know the limit as theta approaches 0, sine theta over theta is 1. So I hope that was helpful. Thank you for watching, and see you next time. Bye.